So in this video we're going to have a look at what we mean by relative atomic mass and relative molecular mass, or relative formula mass. We'll look a little at how we have measured it over the years and how we're going to interpret formulae to calculate it. So, on their way to discovering the modern atomic theory of matter, scientists were beginning to notice patterns in the way that substances reacted. It's likely at some point in your school career you'll compare or will have compared the mass of magnesium oxide produced with the mass of the magnesium needed to produce it. In this experiment, a strip of magnesium is burned in air in a closed crucible to keep in as much of the magnesium oxide as possible and stop it from escaping as smoke. A typical series of results might look something like this. On the bottom axis we have the mass of the magnesium, and up the side we have the mass of the magnesium oxide. And we can see that in this case it appears as if there's a clear proportionality. It would make sense for us to draw a straight line through the results. By measuring the gradient, the steepness of this line, we find that on average every time we do this experiment, the mass of the magnesium oxide is about 1.66 times the mass of the magnesium we burn. In other words, we get 1.66 grams of magnesium oxide for every 1 gram of magnesium we put in. Now let's rewrite this ratio in fractions. 1.66 can be written as 5/3, or 5/3. In the same terms, we could write 1 as 3/3, 3/3. If this is the case, then it's clear that firstly, neither of these elements exist in a continuous state. In other words, there must be fundamental particles, otherwise any combination of the two elements would be possible, like diluting down some orange juice drink. You can have any ratio of orange juice mixed to water that you like. No, with chemicals that react together, it seems as if there's only certain ways in which you can stick them together. We call this the law of definite proportions. Essentially, it means that substances behave as if they're made up of unit pieces like Lego bricks. You can have a model made from 3 Lego bricks or 100 Lego bricks, but you can't have one made from 3.234 or whatever Lego bricks. It just doesn't make sense. So this helps us to come up with the idea that substances were made up from atoms, a basic building block of matter. We can make the assumption that the ratio of magnesium and oxygen are the same as each other in the product. This is an assumption that, of course, we would need to perform more experiments with other combinations of elements to check, but it turns out that in this case it's an accurate one. Evidence from our experiment suggests that oxygen atoms have a mass that's about 2/3 the mass of a magnesium atom. So we start repeating experiments with more and more combinations of elements and looking at the ratios. For example, we can show that copper is twice as heavy as sulfur. Let's imagine that the size of the atoms is proportional to their mass. This turns out not to be quite true, but I'm just using it as a comparative point. These 4 circles represent the figures we have so far. Magnesium is heavier than oxygen, and copper is heavier than sulfur. But we don't yet know about how heavy they are compared to each other. So perhaps then we could try to compare these pairs, maybe by reacting sulfur with oxygen. And in this case we find that sulfur is twice as heavy as oxygen, so we have to double the areas of our right-hand circles to get a better idea of the scales of all of the atoms' masses. And this is where I've obviously screwed up a little bit, because as I start to reorder these, it's not been quite possible for me to get the sizes of the magnesium and the sulfur the correct way around. But let's imagine that I have. We're going from a large circle on the left down to the smallest one on the right. After many more experiments with all combinations of elements that are needed, we find the lightest one of all, hydrogen. There are no atoms that are any lighter, and because of this, we might be tempted to measure all atoms against this one standard. It would be stupid to talk about a 2.5 gram Lego brick and a 5 gram Lego brick and a 7.5 gram Lego brick. If the 2.51 gram is the lightest, it would be more sensible to talk about a 1 unit brick, a 2 unit brick, and a 3 unit brick, etc. This relative measurement is at the heart of relative atomic mass, because it would be a lot easier to work with hydrogen atoms with a relative atomic mass of 1 than to work with their true mass of 1.67 times 10 to the minus 27 kilograms, at least on the lab scale. A basic definition of relative atomic mass, which gets the symbol A subscript R, and that's different from the element symbol for argon because of course the R is subscript here. This definition would therefore be the mass of an atom relative to the mass of a hydrogen atom. Spoiler alert though, this is not going to be the definition we'll end up using. There's always a catch though, because although for most purposes it's easier if we just say a proton and a neutron both have a relative mass of 1, if we want to work accurately, we need to account for the fact that the proton and the neutron have slightly different masses, 1.673 times 10 to the minus 27 kilograms versus 1.675. So hydrogen atoms, however, they're containing only protons, and all of the other elements contain protons and neutrons. So if we used hydrogen as the standard for us to measure against, then we'd start introducing more and more error into our calculations. The more atoms we use, and of course the heavier they were. So how do we get around this? We average out the difference between the masses of the two particles, and the way that we choose to do this is to compare everything to carbon-12. This has 6 of each particle, so the differences between them get ironed out. Based on this definition, the relative mass of the proton and the neutron would be identical. So now we have that the relative atomic mass is equal to the mass of an atom relative to a 12th of the mass of carbon-12. But we're not quite there yet. So it turns out we have machines called mass spectrometers that are able to sort atoms into their different masses. And we find that when using them, even if we put in atoms from only one element, we can often end up with atoms that have slightly different masses. Bromine, for example, is a puzzle because we get 2 different types or flavors of bromine which we call isotopes. They have the same number of protons but a different number of neutrons. One has a relative mass of 79 and one has a mass of 81 in a roughly 50-50 mixture. So rather than picking one of these isotopes as a standard bromine mass and yet again multiplying an error through, it's better to take a weighted average of their masses. What do I mean by a weighted average? Well, if you had 2 types of person in a lift, children and adults, if a child weighs 50 kilograms and an adult weighs 100 kilograms, without any further information, you might just say that it's a safe bet to say that the average mass of a person in there is maybe 75 kilograms. However, if there were 10 children and only 1 adult, that wouldn't make sense. You'd have to add up all of the masses of people and divide by the total number of people. So this is going to help us finish our definition for relative atomic mass. So the relative atomic mass is equal to the average mass of an atom relative to a 12th of the mass of carbon-12. I chose bromine because the figures are close to 50-50, so that the weighted average would still be around 80. But if you look at a more accurate figure for its mass though, you'd find it to be 79.904. So which isotope do you think is therefore slightly more abundant than the other? I.e., of all of the atoms out there, which one is more prevalent, more popular? You can find out the answer by following this link. Now, atoms rarely go around on their own, so it makes sense to have a modified definition for talking about molecules. The relative molecular mass, or formula mass, which has the symbol M subscript R, again, no, that's not Mr., notice the subscript. This would be defined as the average mass of a molecule relative to the mass of a 12th of carbon-12. So if we have a look at this in the context of water, we'd find it has a formula mass of 18, because there are 2 hydrogen atoms, each with a relative mass of 1, and 1 oxygen atom with a mass of 16. A molecule of table sugar, sucrose, with a formula C12H22O11, therefore has a formula mass of 342. Notice that the subscript numbers refer to the part of the formula immediately preceding them. A compound might have brackets in its formula, such as calcium hydroxide. The brackets work in the same way that they do in maths. Everything inside is multiplied by the number outside. So why don't we write CaO2H2? Well, the formula written in this way does not make it clear that this compound is made up from hydroxide ions and calcium ions. The oxygen and hydrogen atoms don't act independently of one another, so it makes sense to highlight the fact that they're grouped together. Imagine the structure of calcium hydroxide, and imagine also how, when it dissolves, the hydroxide ions and calcium ions separate and move independently through the solution, surrounded by water molecules. But the hydroxide ions themselves are not split into hydrogen and oxygen atoms independently. These types of ions, which contain internal covalently bonded atoms, are known as compound ions, Others you should know include SO42-, the sulfate ion, NO3-, the nitrate ion, CO3 2-, the carbonate ion, and NH4+, the ammonium ion. And this brings me to my final point. There's a potential issue with the phrase relative molecular mass, or RMM. You'll often hear me use these out of habit, and I'll always use the shorthand symbol MR, but I prefer to use the phrase or formula mass, and the reason is this. When you talk about the relative molecular mass of water, it's a simpler thing to add up the masses of the water's 3 atoms. With an ionic substance like salt, or with a giant covalent substance like diamond, however, it doesn't make sense. Let's think about diamond. Every atom in the structure is covalently bonded to 4 other atoms. All of the atoms in any crystal of diamond are bonded covalently together, so in a way we could talk about each crystal of diamond being kind of a giant molecule, or a macromolecule. There'd be no sense, however, in reporting a different formula for each molecule, as then we'd never have a consistent formula for diamond, and, well, it would just be such a hassle. So in the cases where we have giant structures, such as sodium chloride, iron, any metallic structure, ionic structure, or giant covalent structure, we report the simplest whole number ratio of elements within this structure itself. Just don't ever fall into the trap of thinking that if you see MR of sodium chloride equals 58.5, that means that there's a diatomic molecule of sodium chloride floating around. Of course it isn't. That's the empirical mass, essentially, the formula mass. And that's why I don't really like the phrase molecular mass or relative molecular mass, because people can get a little bit confused.